So what I'm going to talk about today is the refinement and validation of atomic models in cryo-EM maps using our software TEMPy2. And since I'm in the last day of the conference, you probably heard quite a lot about the status and the state of cryo-EM these days. So I started working in the modeling in this field nearly 20 years ago. And so the field has changed a lot, and I want to show you a few things that we showed and developed over the years and what we have currently in our TEMPy2 software. Let's see if it moves. Just a second. Okay. So I have not seen all the talks, so I don't know who have shown what, but you probably know and understand the current state of cryo-EM. And you also know that the resolution revolution, so-called, happened around 2013, 2014, when the direct electron detectors came, and also we had a lot of improvements in image processing software, and now we have more and more of that, of course, with machine learning. And of course, what happened was that we started, relatively speaking, we started having many more maps and resolutions that are better than 10 angstrom. And you can see the largest increase is actually in the range of resolution around 3 to 4 angstrom. And as a result of that, we started seeing more and more atomic models deposited together with the cryo-EM maps. And of course, there is an exponential increase, and it's still growing. We see more and more the position of atomic models corresponding to cryo-EM maps. So the position of the atomic models is in the PDB, and it corresponds to atomic models in the electron microscopy data bank. Now, to understand how to use these cryo-EM density maps, we need to understand that with cryo-EM, we actually get a range of resolution. And in fact, we get this range of resolution not only in different maps, but as you probably heard a number of times in the last few days, in the same map itself. And you can see this is currently the division. This is of all the maps in the EMDB. We have already 33% of the maps or at 3 to 4 angstrom resolution, and actually more than 50% of the map, or 60%, are better than 6 angstrom. So there's a lot to do. However, we still have quite a few maps from subtomogram averaging or from very flexible structures where we have maps at lower resolution. So really, depending on the resolution that we're dealing with, we need to come up with different approaches. And originally, when I started working in this field, we were talking more about 10 angstrom, around that range, 15 angstrom. And now we talk more and more about the near atomic resolution and even the atomic resolution. Now, depending on the level or on the resolution, we have to consider that we look at different part of the structure that can be fitted, or not different part of the structure, but different structural elements. So, for example, if we are at a lower resolution range, we can think about fitting all subunits or whole proteins. And as we go higher and higher in the resolution, at around 8 angstrom or 10 angstrom, we can think about fitting long helices. And our Gamma TEMPy software is a software that was designed to do rigid body fitting of these large elements. And as we go into the more medium resolution range, we have a tool that we recently developed that is called iTEMPy, that works together with Chimera X. And finally, when we get to even higher resolution, we have our TEMPy-Ref software, where we can also calculate B factors. So I'm going to walk you through the possibilities that we can have with our software now, and I'll start with talking about TEMPy in general. So TEMPy is a modular Python library, and we're using other libraries like NumPy and SciPy and Gemi for structural operations, atomic structure operation. We're using matplotlib and also OpenMM for refinement. And we published many papers over the years. This is just some of them that helped us to come up with a philosophy of what we have in our software TEMPy. So I just want to say that the first thing, that the most important thing, in my opinion, is actually to know how to validate your structure. And I see Chu over there, and he's one of the pioneers of this idea of the fact that we actually have to look how well these structures fit in the density map. And if we just do fitting and we don't check how well it fits in the map, then we end up depositing structures in the data bank that have a lot of errors. So what do we do and what do we have in TEMPy for that? We have many scoring functions. I think we have something like, we counted today, something like 26 different scoring functions to assess the quality between the goodness of fit between the atomic model and the density. Some of them actually are based on the envelope or on the surface of the protein. So we're matching surfaces. I'm not going to go into it, but some of them are the standard ones, of course, and the cross correlation is one of them. And the mutual information that we often find works better at low resolution is another one. Now, what's important to understand is that we shouldn't really just look at the global assessment of the structure. And when we look at one region of the structure and we calculate the correlation, we can get with our model one number. However, if we look in another region of the structure, we may end up with a much lower correlation. And this could be for many reasons. It could be that depending on the local resolution and also on the quality of the models in this region. Now, for this reason, quite a long time ago, we decided that we should start looking at the correlation locally. And initially, we did it because of the level of resolution that we were talking about. At the time, the maps that we were achieving back then, we looked at elements like secondary structure elements or whole domains. And we were looking at it with a segment-based cross-correlation coefficient. But later on, we decided, as the resolution got better and better, that we can start looking at it at the level of the amino acid. And Agnel Joseph, who is now at STFC developing the CCPM package, he developed the SMOC score at the time, which the idea was to actually either look at overlapping windows and center it on a given amino acid, or later on we also developed it specifically around the amino acid. But it's simply correlation, but is looking at a specific given amino acid. And the usefulness is of course that there are regions that have worse fit for various reasons. And if you just look at a single amino acid, you can identify if this amino acid is outside the density or if the whole region, for example, because then you will see that the SMOC score is going to be lower. And just an example, this is one of the early structure that was deposited in the PDB for SARS-CoV-2 spike ectodomain. And this is still deposited in the EMDB. And what you can see, if you just simply run the SMOC score, you can see that you have low correlation at the certain region. So it's not just one single amino acid, but it's the whole area of the receptor binding domain is actually badly modeled. And if you look more closely, you can see that in fact the model is not very well correlating with the density that you see in this region. Now we also 2 years ago we assessed all the models that were deposited for the CASP target, the cryo-EM CASP target, and what we found was that nearly all the scores exhibit a relatively high degree of correlation across all targets. So this is just one example of a phage RNA polymers, but what we saw this similar matrix with all the different proteins that we looked at. And you can see these are, maybe you may or may not heard of these scores, but some of these scores are actually purely structural accuracy scores, like the LDDT or the DDTTS. And you can see that there's very high correlation of our global scores and also of our smoke scores with that. The only score that we didn't see good correlation is the EM Ringer. And I think EM Ringer probably does not work very well when when the models are pretty far. They are not really near native models. And that's the reason that we don't see correlation there. But pretty much all the Phoenix scores and all the RMSD, LDDT, and all these RMS-based scores are, or distance-based scores, or sorry, from the structure that is modeled from the EMAP, they are all correlated very well. We didn't put the Q score here. It was difficult to use this at the time, but I'm just showing down here that actually the Q score also correlates very, very well with the smoke score. We find exactly the same regions that are not very well modeled. Okay, so just to summarize what we have in TEMPy for in terms of scoring function, we have global scores, and I mentioned some, and we have what we call segmented scores, so like the segment-based cross correlation coefficients. So if we want to segment it based on a helix or based on a domain and so on, and we have a residue-based score. And we also, I didn't talk about it, but we also have in TEMPy a sort of a local FSC score. So we calculate it in Fourier space, and this is what you see here. We call it log fit. But pretty much all these, as I said, all these scores are correlated with each other. And whatever you choose, it's important that you measure your model or look at the accuracy of the model or the agreement of your model with the map, not just globally, but also locally. Now, finally, I just want to say that we a couple of years ago with Sonny Malhotra, who's also now at CCP-EM, we developed a score, a machine learning based score. So it's based on support vector machine, looking at features, at protein interface features, and from high resolution X-ray structures. And what we did in that paper was we assessed all the cryo-EM models, and we looked if we found both scores and also based on the PI score. We call this PI score. Now this was only on the interfaces. So this is not, we're not looking at the full atomic structure of the protein, but we're just looking at the interfaces, because what we realized is that often there are errors around the interfaces, and these errors occur partly because there are many maps that are constructed by composite scores, and this is something that I don't have time to talk about today, but there are errors in the maps themselves, in the composite maps, and if you start looking at that in the EMDB, you will find problems with those composite maps. However, we just looked at it here in this paper, we just looked at it from the point of view of the model, and what we found is that sometimes the smoke score, for example, here, this is an example of a 10 angstrom resolution map. We've shown this also in higher resolution maps. I'm just showing it at the 10 angstrom. What we found is that sometimes there are regions that the smoke score is going to tell us that the interface is good. However, the PI score is able to identify that actually there is a problem in the interface. And that's why we decided to combine the PI score together with our density-based score. So we're taking features that we know from the knowledge of what interface protein structure should look like, and we add them to the knowledge that we have with the smoke score, or with smoke score, or with any other density-based score. And recently, some other researchers found that PI score is actually quite useful for assessing interfaces from structures of AlphaFold, independent of the density, but that's not relevant here. Okay, so our software, just to say our scoring, TEMPy scores and also the PI scores are, the PI score is actually in the CCP-EM package. If you don't want to use TEMPy and you just want to use the CCP, use it via a GUI. We have the global scores, some of the global scores, we have some of the local scores, like the smoke score. And in general, Agnel Joseph, who I talked about earlier, developed a whole pipeline for validation that is part of the CCP-EM package. So you can look at geometry, you can look at the Kablam score, you can look at the secondary structure prediction and see if it correlates with your or agrees with your density assessment of your model. And it really helps you to identify regions that have a problem in your that have problems in your model. And as I said, you can also run the PI score via CCP-EM. Okay, so now that we know about validation of our models, the question is, what do we do with fitting? So the first thing is to do rigid fitting or multiple component fitting. And for that, we've some time ago, we've developed TEMPy software. And I just want to say that it exists in the TEMPy package, but I'm not going to talk about it too much today. Basically, it uses a genetic algorithm or Monte Carlo, or in the original paper, we talk about a genetic algorithm, but we added since then a Monte Carlo method to do the optimization. The method performs pretty well at 10 angstrom resolution and even down to 15 angstrom resolution. It's less good at 20 angstrom resolution. But now this problem, of course, given the current situation with structure prediction, has become less relevant for very low resolution. Now, the scoring function that we're using with TEMPy that we found useful was the mutual information. However, we also use a penalty score when we make sure that the components are not actually clashing with each other. Okay. Now, what I really want to talk about more is our refinement software or refinement methods. So, of course, you can rigidly fit the structure in the map, and you can play with the positions of the structure. But what's really interesting about cryo-EM is the fact that we can identify multiple conformation or different conformations compared to, for example, the crystal structure that we have, or if we predict our structure by protein structure prediction methods that not always will predict the correct conformation, if you like. So what do we do in this situation? So we have two methods I will talk about. It's originally we had actually and what I'm going to show you is that actually what we do is we interactively refine the structure and also look at those scores that I was discussing before. So originally, a long time ago, we developed the method, the FlexEM method. This was still part of the modeler package, and the idea was that we can actually combine the force field or the, if you like, the stereochemical, the non-bonded, the violation of the stereochemistry and the non-bonded contact together with the cross correlation. And we move the coordinates according to this force. And this is the origin of our concept. But what we did at the time, because we had a lot of maps at this intermediate resolution, and 10 was really in 2006, I think, when I started developing it, 10 angstrom resolution was really a standard resolution that you would get back then. So we said, okay, we shouldn't really move individual atoms at this resolution without any additional constraints, because of course we're going to do a lot of overfitting by doing that. And so the concept was that we are going to select rigid bodies, and we're going to move these rigid bodies and then refine the loops together, and we do all of this simultaneously. And just to say that FlexEM is still working, if you wish, and it's part of the it's part of the CCP-EM package. Now here, for example, in this example, you see FlexEM refining a structure into a 10 angstrom resolution map. This is a simulated map. Now you can see that the refinement is not perfect, because we build a homology model that is very, very from very low sequence identity. Now, this is a long time ago. Maybe if we build a structure now with AlphaFold, it would be a very good structure, and we won't even see this bend here in the helix. But what's my point here is that we didn't refine the helix inside the helix, because we simply don't have enough information, correct information in the map to do that. Now, to understand how to define those rigid bodies, we developed an approach that is clustering of secondary structure element with a number of parameters. And that really helps us to define those rigid bodies more automatically rather than doing it individually. Of course, when you use this concept of FlexEM, you can define your rigid bodies as you wish, but you could, if you wanted to do it automatically and have some sense in terms of the way the structure looks like, you could use this Refinement rigid body, which is essentially structure clustering of secondary structure element. And what you do is once you do that, you can actually define your rigid bodies based on Refinement, and you can pull that into the density. And recently, we haven't published it yet, but we have a new server for it where we also do RNA clustering. So feel free to use it and try and cluster your RNA structure if you're interested. Okay, so now using this concept, even at 5 angstrom resolution, which was back then something that the reviewer even said to us, why are you even doing that? But we tried also of course at lower resolutions, but this was the highest resolution that we tried. And what we could see is that if we start with an initial structure, and so this is a structure in 2 structures it's the same structure, a different conformation. So the yellow has to be refined to the map that is in a different conformation, represented by the white ribbon. And if we look at the RMSD of the initial structure, it's going to be 12 angstrom RMSD from the from the target structure. Now, if we don't cluster it in what the secondary structure element, which is what we've done here, and we run at the time it was FlexEM, but it can be any other refinement method, we are ending up at around 3.7 angstrom for RMSD. However, if we first cluster it based on Refinement, so this cluster that you see here, and then we uncluster the secondary structure and do further refinement, we are getting to a much better result. So that tells us that this hierarchical refinement is actually quite important to do and make the optimization much more efficient when we have situation where the conformational change is quite large. And Agnel, again, what he did is he updated at the time FlexEM to work in a higher resolution, slightly higher resolution. And this is an example of a map of Goriel at 4.2 angstrom resolution, where what we did was he started by the initial structure is in a completely different conformation. This is in blue here, in light blue, and in gold you see the structure that corresponded, the structure that actually deposited in the PDB corresponding to this map. And we are starting using these Refinement rigid bodies, and you can see that the optimization goes very quickly into a closer solution. It converges much quicker this way. And then we let the secondary structure, and then we do an all atom, and we find that we really reduce the overfitting by using this approach. Now, fast forward a few years later, and we decided that we will develop the same approach. So we still use FlexEM, but less. A lot of software has been developed since then, and there's a lot of great visualization programs like Chimera and Chimera X nowadays. So we decided to take the same concept, and now Tom Mulvaney, who is a PhD student in my group, decided to use SMORC together with this idea of the segments fitting or rigid body fitting and then refinement in Chimera X. So he developed a plugin. This is not yet available, but you can email us if you want. But we are writing the paper now. But basically what we're doing with TEMPy is we first identify the regions that have low quality of fit. We inspect those regions, we select the rigid body that we want to fit, and then we shift it. and then we apply forces to refine it using OpenMM that is working very well with Camera X. So just to show you a little better, here's the smoke score that I was describing earlier, where you can really look locally at the positions of specific amino acids. You can see we're also coloring it based on the smoke. So you can see that red means bad, and it's outside the density. And then what we do is we select the region. We can select the regions of bad fit with the density. And you can zone if you wish. So you can really utilize together with this plugin of TEMPy all the routines that you have in Chimera X for density. So you can really visualize those specific regions that have a problem. And then we can use a tool that is called the Ghost tool, where we select this region, we create another tool, and we can move, and you can use those Chimera X features to actually either fit it manually, or we can use Chimera X tools for automated fitting for this. And then we can actually, finally, sorry about this little typo here, finally, we can actually do the refinement. So I'll just show you how it works, because these little movies. So these are, then the forces are applied. This is, it's not the program NBFF, sorry about this. This is a mistake, but it's actually, we're using forces with OpenMM to pull, we basically fit it rigidly in a position in the density, and then we're using harmonic restraints to pull the structure from its original position into the new position. So in that way, we are using the OpenMM, using OpenMM. So we're actually using a force field to make sure that we are keeping everything at least in correct geometry. Okay, and just another plugin that we developed in Chimera X is the Refine, and that actually is already available if you want to use this, not for the RNA but for the protein. So and what Tom did was actually to add Refine to Chimera X, so you can select those rigid bodies automatically. So you have, in a way, two ways of selecting rigid bodies. One way is doing it based on your correlation, so your smoke score, and you select the regions that don't fit very well. Another way is to use the Refine clustering program and select those sets of rigid bodies that you're interested in, and you can use exactly the same optimization program to improve your structure. Okay, so finally, what I want to talk about is what do we do when we get to higher and higher resolution, and what do we do with maps that have of course, uneven resolution or uneven distribution of the resolution. And we also developed another software recently, which is called TEMPy-Ref. And what we do with TEMPy-Ref, we're actually using expectation maximization approach, using a mixture model to describe the model in the map. And our variance is the B factor as a result of that. So we can calculate B factors in our optimization. And the paper is in bioRxiv if you want to have a look. And again, here we are using the routines of we're utilizing OpenMM for our molecular dynamics simulation, and we are improving the structure in this way. Now, what we did is we refined at the time that we started doing this. There were 366 cryo-EM maps or models that are in maps in the EMDB that were also refined automatically by the Sears server, which uses Phoenix to automatically refine all these models that correspond to models in PDB that correspond to cryo-EM maps in the EMDB. And what we decided to do is actually to use an ensemble representation of our refinement result instead of using a single structure. And what I'm showing here is when you're doing that, actually your ensemble map is much more similar to your experimental map than looking at a single refinement. And this is why we're getting a much higher correlation compared to what you get from Phoenix, which is what you see here in green. So the original models that are from PDB have a much larger cross-correlation, range of cross-correlation. And after Phoenix refinement, you can see that this is the green overall. And then when we're looking at our ensemble representation approach, we are getting a much higher correlation. Now, even when we do a single model, I'm not showing it here, we're still getting our refinement are as good as Phoenix in most cases, or either similar or slightly better in many cases. However, our geometry, so if we're looking at mole property, we're somewhat worse than Phoenix. However, in Phoenix, of course, as you know, there is restraining on the geometry. So, for example, by default, it's using the Ramachandran plot and other restraints to make the geometry better, if you wish. So this is the reason you see that. But of course, if you look at the models that are coming from PDB, the quality of this model is really all over the place. Okay, so just another example that we're showing here, that I'm showing here, is using this approach of ensemble representation, which I'm sure you've heard quite a few times over the last few days. But I'm showing this example because it's really nice. You can really see this histidine into conformation. So we're starting potentially to look at multiple occupancies here. And we can see this also in another example. These are all examples of models from the PDB. And for example, if you look at this nucleosome example, you really see that the bases are not well refined in the structure that is deposited in the PDB, but we're able to refine it better using our approach. Okay. Finally, I just want to say something that you already probably all know, which is the combining the cryo-EM data with AI-based structure prediction can be very powerful. So Tristan, who developed TEMPy2, not sure if I said it before, Tristan is now not in my group anymore. He's moved and became a lecturer at Berkeley College in London. But 2 years ago, we refined all the CASP-14, the previous CASP cryo-EM targets, and we used TEMPy2 for that, earlier versions of TEMPy2. So we didn't do the ensemble representation back then, but it's the same software. And we did all the things that I've described here. This is and we computed the scores, and we did. So we looked at all the scores from the models that came from CASP, and we also refined using TEMPy2, refined all the models and looked at the scores after doing the refinement. And overall, we refined 13 single domains and 5 multi-domain proteins. Okay, now these are the structures that we refined. These are the different targets. And what's interesting, if you look on the right-hand side, is that these are all the initial structure, and we are not looking at all CASP models. We are looking at high-quality CASP models only. Otherwise, it will be really beyond this plot, because some of the models that was deposited were very, very bad. So we only took models that had quite good GDTTS and LDDT scores. And we refined, these are the scores that you see. This is the cross-correlation for initial ones, and then we refined them. Now, the structure, the reference structures coming from the authors is in blue. And I should just say that what we did was fully automated. So we didn't really interfere at all in the structures. Whereas when it comes from the reference structures, people used CUT and made sure that their structure is nice and so on. But you see that actually, in some cases, our best refined structure is better than the reference structure. Now, the initial model is actually are actually models coming from CASP. In most cases, it was AlphaFold, but it wasn't all the cases, because AlphaFold didn't participate in every specific or in every target. So I don't know which one is which here, but all I'm saying is that having really, really accurate structure prediction model sometimes can result in a better final refined model than just using less good approaches for modeling. Okay, so where are the errors? And if we look at what AlphaFold predicted in this particular case, this is again this RNA polymerase from a phage, I think. What you see is that, and this is another example of the flagellary. You can see that the domains here on the left-hand side, you can see that the domains are both predicted really, really well. What's not predicted well is the linker between the domains. So what actually happened was that this is a subunit from the RNA polymerase. But when they were modeling this subunit, they did not model the entire RNA polymerase. So there is no context for this protein. And we haven't actually tried it since then, but it could be that if we use AlphaFold to model the entire polymerase, this subunit will actually be in the right place. But if you just use it without the context of your complex, you may end up with having wrong orientation between the domain that you are modeling. And it's the same holds on the right-hand side for the flagellar ring, for example, because this is a complex and we are only modeling one individual subunit. So the secondary structure, the hairpin, is correctly modeled, but it's not correctly oriented. Of course, this is very much the case also when we talk about errors in loops, and people who are using AlphaFold or Rosetta Fold or any other of these new methods for modeling should be really, really aware of that. And that's why it's still great to have cryo-EM structures, because they can really help us to refine those regions. And interestingly, what we found, and this is a 3.8 angstrom resolution, that's a region where you do really get a lot of errors, especially in loops, because the side chains are not very well defined in many cases. So what you see here that is interesting is that the regions that we found the most variability between the models that were deposited to CUSP also correspond to the regions that were more difficult to refine, and also add also errors in the final structure, or in the reference structures, in both actually. And that kind of makes sense because we expect more variability and more errors in loop regions, for example, regions that are more flexible. Now, finally, I just want to show that why is it useful. Another example is what Tristan did was to take, again, a model deposited in the PDB. And this is the RNA, again, from the RNA polymerase, RNA-dependent RNA polymerase from SARS-CoV-2. So it's a relatively recent structure. And the resolution is 2.9. And if you model it with AlphaFold, you can see that there are some regions that have really, really bad correlation with the... sorry, this is the AlphaFold LDDT. You can see that there's regions that AlphaFold is not very sure about. Now, this is the deposited model. Now, and if we take this model and we put it in the map and we refine it, what we find is that we can actually fill in some regions using the knowledge of the density. And the smoke score actually help us to define which, and based on a threshold, we can decide, okay, this is going to be the model that we will include in the map, and these regions that are not in density at all are not going to be included. And we can, of course, correlate it with the confidence in AlphaFold models, but what we really want to stick to is the agreement with the density. So we could actually expand this model quite a bit by doing this. Okay, and then I just want to finish by thanking my group, a lot of people in my group, of course, and here in Hamburg, and lots of thanks to the people I mentioned on the way, especially Tom and Joe, who are working on TEMPy continuously, Tristan, who I mentioned just recently left, and then Agnel and Sonny that are now in CCPEM, Andrei Kristofovic, who is doing everything in CUSP, and Daven, who was the first student who started TEMPy many, many years ago, and Arun, who used to be a postdoc in my group and developed gamma TEMPy initially. And thank you for all the funding, and thank you for listening. I'll be happy to take questions.